next, we will discuss the conformational isomerism in cyclohexane. So cyclohexane, you know that hex means 6 carbon atom and ANE means that it's an alkane, and cyclo means that is cyclic in structure. So that means cyclohexane contains 6 carbon atom. All carbon atoms are saturated. That means all carbon atoms forms carbon-carbon single bond, and that is a cyclic structure. So we normally represent cyclohexane like this. So when you represent cyclohexane on a paper, for example, in your examinations, we normally represent cyclohexane like this, where all these coordinates are carbon atoms. So 1, 2, 3, 4, 5, 6 carbon atoms, and each carbon atom has 2 hydrogen atoms attached to that, so which are represented like this. But so if this is a hexagonal structure, so it's a hexagonal structure means the bond angle is 120 degree. Okay, but the problem is all carbon atoms are saturated, or all carbon atom forms on only single bonds. That means the hybridization in each carbon atom is sp3 hybridization. So sp3 hybridization, we know that in sp3 hybridization, the geometry is tetrahedral and the bond angle is 109 degree 28 minutes. But in this hexagon, the bond angle is 120 degree. So that means for cyclohexane to exist in hexagonal shape, there will be a strain arising because of the difference in the bond angle. Because the carbon atom in cyclohexane is in sp3 hybridization and the tetrahedral geometry which that carbon atom prefer. But to form a hexagonal structure, the bond angle has to be 120 degrees. So the difference between the 120 and the ideal sp3 bond angle of 109 degree 28 means that causes a strain to this structure, and that strain we call it as Bayes strain because the scientist who proposed his name is Bayes. So the cyclohexane has Bayes strain. So that means cyclohexane with this structure will be unstable and that will react immediately. But in reality, cyclohexane is very stable molecules. So that means the actual structure of cyclohexane is not this one, even though we use this structure to represent cyclohexane for our convenience. But if you analyze cyclohexane stereochemically or three-dimensionally, cyclohexane structure is not like what is written here. So then how cyclohexane is existing in nature? So cyclohexane actually twist its shape and take 2 conformations. So to reach the ideal bond angle of 109 degree 28 minutes, cyclohexane will twist its structure or pucket structure and take 2 major conformations. So we will discuss what are those 2 conformations. So the first one is the chair conformation of cyclohexane. So this is the representation of cyclohexane in chair conformation. So here the yellow colored are the carbon atoms at each corner or each junction. Okay, so you can see that forms a shape of a chair. Okay, so here the bond angle is 109 degree 28 minutes. You may not feel that all bond angles are 109 degree 28 minutes by seeing this picture, but however, if you make a model of cyclohexane with this structure, then you will realize that all bond angles are 109 degree 28 minutes. So this is a twisted structure in 3-dimensional plane, and all carbon atom has other hydrogen atoms. So I have mentioned some of the key factors of this chair conformations. One is the hydrogens on adjacent carbon atoms are staggered. So in these chair conformations, so if you take this carbon atom, see the adjacent carbon atoms of this carbon atom are this one and this one. So the hydrogen atoms in this carbon atom and this carbon atom and this carbon atom all are staggered conformation. So we know what is staggered conformation now. Staggered conformation means all hydrogen atoms are far apart. So that gives the molecule a stable conformation. So that means the chair conformation of cyclohexane is highly stable because all hydrogen atoms in adjacent carbon atoms are staggered in nature. Okay. So other thing which you have to notify is here all are hydrogen atoms. That's true, but I have represented some bonds with red color and some other bonds with black color. So the black colored hydrogen atoms or bonds or hydrogen atoms are axial hydrogen. So axial hydrogen means all these black colored hydrogen atoms, which I represented here, they are parallel to the molecular symmetry axis of this cyclohexane. Don't worry about those kind of stuffs, but anyhow, these are axial hydrogen atoms. So you can count 1, 2, here I'm starting from here, 1, 2, 3, 4, 5, 6 axial hydrogens. And also you have equatorial hydrogens. You have 1, 2, 3, 4, 5, 6 equatorial hydrogens. So in cyclohexane, the hydrogen atoms in each carbon atom, it could be, there are axial hydrogens as well as equatorial hydrogens. Okay. And we represent cyclohexane on a paper like this, because this representation is time consuming. So you can also represent cyclohexane like this. So here the carbon atoms are numbered 1, 2, 3, 4, 5, 6. And each carbon atom has 2 hydrogen atoms, and one is in axial position, the other one is in equatorial positions. If you examine all the carbon atoms, you will see the condition is the same. So here, this is a stable conformation of cyclohexane, where the hydrogen atoms on adjacent carbon atoms are staggered in nature. Now, the interconversion of this conformation is possible. So there are 2 main chair conformations which can be interconvertible, and both chair conformations are equal in energy. So that means this interconversion is very easy. So we call it as ring flip. Ring flip means, for example, take this chair conformation of cyclohexane. Here you can see that all red colored hydrogen atoms are axial and the black colored hydrogen atoms are equatorial. So this conformation, after ring flipping, you will get this conformation. So what's happening here is, when a ring flip is happening, all the axial hydrogen atoms becomes equatorial and all the equatorial hydrogen atoms becomes axial. So if you examine these 2 structures, you can see that in the first structure, all red hydrogen atoms were axial, but after ring flipping, all red hydrogen atoms became equatorial, whereas the all black hydrogen atoms, previously those hydrogens were equatorial, and after ring flipping, they became axial. So this ring flipping is possible in cyclohexane, chair conformation of cyclohexane. Okay, now, so this is about the chair conformation of cyclohexane. So you may think that in the previous lecture, I told you that conformation isomerism arises by the free rotation of carbon-carbon single bond, and those conformation, what we call the those isomerism, what we call the conformational isomerism. But here you cannot see any free rotation of carbon-carbon single bond, but rather it's a twisting of the structure, twisting of the structure that gives you a conformation. That gives you, yes, conformation. So this is also called conformational isomerism, because to go from this structure to this structure, you don't have to break a bond and form a new bond. So there is no bond breaking and bond formation is happening. So only by twisting the structure of the molecule, it goes from one isomer to the other isomer. So this is about the chair conformation of cyclohexane. Next, we will discuss about the second most important conformations of conformation of cyclohexane, which is the boat conformation of cyclohexane. So here I have represent the boat conformation of cyclohexane. So in boat conformation, the molecule take the shape of a boat, and here also you can see that each corner is occupied by the carbon atoms, 6 carbon atoms, and this conformation also have the hydrogen atoms. One is axial hydrogen atoms and equatorial hydrogen atoms. But when compared to the chair conformations, this boat conformation is less stable or higher in energy, almost 29 kilojoules higher energy than the chair conformation. So why? Let's examine why the boat conformation is less stable or higher in energy than chair conformation. That is because mainly 2 reasons. The first reason is the the hydrogen atoms on second and third carbon atoms. So hydrogen atoms on this carbon atom and this carbon atom, second and third carbon atoms. Also hydrogen atoms on fifth carbon atom and sixth carbon atom. So that means fifth one and sixth one. So the hydrogen atoms on these four carbon atoms, they are in eclipsed form. So that means all the hydrogen atoms on these carbon atoms are very close to each other, which you may not get that feel from this picture because as I told you in a previous lecture as well, when you examine this structure, you can see that there are plenty of space between these carbon atoms, but in reality, or if you make a model by using ball and stick, then you will realize that there won't be this much space between these carbon atoms, and you will clearly understand that these hydrogen atoms are very close to each other. So the hydrogen atoms on second and third carbon atom, and for fifth and sixth carbon atom, they are in eclipsed position. That means those hydrogen atoms are very close to each other. Therefore, there is steric hindrance or crowdedness will be there. So that makes the molecule discomfort or higher in energy. The second reason is the closeness of flagpole hydrogens at C1 and C4. So if you see the carbon atom, the first carbon atom and fourth carbon atom here, one of the hydrogen atoms attached to these carbon atoms, for example, this hydrogen atom, for example, for the carbon atom, first carbon atom, and this hydrogen atom for the fourth carbon atom. So these two hydrogens, we call it as flagpole hydrogens because it's like a flagpole, and these hydrogen atoms comes closer. These hydrogen atoms come closer because of this boat conformation. So that also makes the molecules less stable because of the steric hindrance. Here also there will be steric hindrance. So these two steric hindrance or crowdedness makes boat conformation less stable or higher energy, almost 29 kilojoules more higher energy than chair conformation. So if you compare the chair conformation and boat conformation of cyclohexane, the chair conformation is more stable than the boat conformation. Okay. So we will see what is the conformations of methyl cyclohexane. So methyl cyclohexane is if you substitute one of the hydrogen atoms in cyclohexane with the methyl group. So that is methyl cyclohexane. So here the situation will be where the methyl group, how the methyl group will bond to the carbon atom. Either it could be axial methyl group or it could be equatorial methyl group. Then we will compare the stability of these two structures, these two conformers, which conformer is more stable than the other conformer. Okay, so let us examine the methyl cyclohexane with where the methyl group is in axial position. So here you can see that this methyl group is in axial position. So what you can see that I have numbered this carbon atom as number 1. And the next one is number 2 and the other one is number 3. So if you compare the first carbon atom and the third carbon atom, so the methyl group is in the first carbon atom, here is CH3, then second, third. In third carbon atom, there is a hydrogen atom in axial position. Okay, so these two groups or these two species, they are very close to each other. Similarly, if you go in this direction, that means third, fourth, fifth. So this carbon atom, if you look at this carbon atom, here also there is an axial hydrogen. So my point is these two hydrogen atoms, one is at the third carbon atom, the other one is at the fifth carbon atom. These two axial hydrogens, they are very close to the methyl group in this carbon atom. So again, you have to remember, I have to keep one point in your mind that the distance, what you feel from this picture is not the actual distance between the carbon atoms. In reality, these groups are very, very close to each other. So what will happen is this methyl atom will come in close with the hydrogen, axial hydrogen on third carbon atom and the axial hydrogen on fifth carbon atom. So we call this interaction as 1,3 diaxial interactions. 1,3 diaxial interactions. Why it's called 1,3 diaxial interaction is starting from this carbon atom, if you go in this direction, this is 1, 2, 3, third carbon atom. And if you go in this direction, 1, 2, 3, even though the carbon atoms are numbered 1 to 6, if you go in two directions, the carbon atoms, the hydrogen atoms attached to those carbon atoms which interfere with this CH3 are at the third position. So that's why it's called the 1,3 diaxial interaction. 1, 1, 2, 3, and 1, 2, 3. Okay, so these axial hydrogens will interact with the CH3 group, and that makes the molecule more discomfort, and it has slightly higher energy than if you compare the conformer where the CH3 group is in equatorial position. So here you can see that since the CH3 is in equatorial position, none of the hydrogen atoms can interfere, come close to the CH3 like in this conformer. So in this conformer, its energy will be slightly lesser than this conformer, and its stability will be more. So if you compare the methyl cyclohexane, compare between where the methyl group is in axial position and methyl group in equatorial position, the methyl group, the conformer where the methyl group is in equatorial position will be more stable than the other conformer, because when methyl group comes in axial position, there is 1,3 diaxial interaction, which makes the molecule less stable. Okay, so this is all about the conformational isomerism in ethane cyclohexane and methyl cyclohexane.